I hope it works. First, starting, I want to give credit to students who worked in the last years on this topic I will present here. And furthermore, I've done a lot of the results I present here in close collaboration with Rudolf Friedrich from Münster. He's a theoretician, I'm experimentalist. And furthermore, I will use a lot of very nice data from the helium group in Grenoble, where I stayed some years ago and got introduced into turbulence. And I'm from my background, low temperature physicist, so I was really excited yesterday to hear what is going on with quantum turbulence. And I want also to give some credits to Christos Vasilikos, from whom I got measurements. We made measurements from the fractal grid. Well, I'm not only working with low temperature, it's falling down. This I have skipped now. My background nowadays, I apply also quite excited turbulence insights as the impact on turbulence of wind turbines, which is, I think, a quite nice new aspect, which may give also some future application of our insights we get into turbulence. But on the other side, I work also on small scales. We develop new sensors, which are based on this scanning force microscope. So you can make really tiny sensors where you can go up in 10 micrometer size of measuring, 100 micrometer size of measuring the velocity fluctuations in 2 dimensions. But okay, I just want to give you at the beginning some indication where I'm working experimentally. Now my talk will switch over more in analyzing data and getting out some new aspects on turbulence. First, I will summarize shortly. I have not much to say about isotropic turbulence. I will go into multi-scale statistics, which was nicely introduced by the talk just before me now. And I will show you a Fokker-Planck equation for the stochastics of turbulent disorder. And then bring up some new features like new length scales, Einstein-Markov lengths for turbulence, and discuss a little bit the universality of turbulence. Well, I think the challenge of turbulence is always still that we should understand the disorder, and we end up, if we get it, the endpoint statistics, knowing what the probability of a velocity at that point is, we somehow have a good description of turbulence, I think. We know the 1-point approximation. This is first thing you want to know, the mean flow, how it's distributed with the Reynolds average, Navier-Stokes equation, and so on. We stick a lot of time in the last decades in the statistics of 2-point correlation done by the velocity increments. The statistic of velocity increments is nothing else than somehow considering 2-point correlations. For the 2-point correlations, we know from Kolmogorov, from the pioneers, we have already some results on which we stick, which we try to improve, which we work on. Also, I want to point out this nice result from Karman-Horvath, which is finally linking the transversal and the longitudinal velocity increments, directional 2-point correlations then somehow. Okay, I want to step further. My interest is, I want to have the n-scale statistics, which was just introduced in the talk before. I want to know something, the cascade, what it is, but the structure, the disorder of the turbulence on large scale and small scales at the same time, and all different scales. I want to have the joint distribution of all this. Then I have at last for this disorder with respect to increments, a more complete description. So the question is there a simplification possible? I changed the notation. Ui is just always an increment, yeah? Because I don't want to write uri and so on. If I write ui, it's with respect to the distance ri. Okay, is it possible to get something like this? General. Well, you can go on mathematically. Bayes' theorem, the joint probability, if you know the conditional probability, it's the same. If you have all the conditional probabilities, you know also the joint probability of the statistics of n-scale velocity increments. Well, There may be a simplification if the multiple conditioned. So you condition on all the structure up here and ask what the statistics on the smallest scale will be. So you may ask, is it necessary to know all way up, all the structure and larger scales? Or maybe you can forget some? Or is it even that the statistics on the smallest scales, which was just discussed at the end of the last talk, is independent on larger scale structures? If this would be the case, we would be fine with a description of single point distribution. Well, you can look experimentally at it. You can measure a double condition probability, just fixing the velocity fluctuation on that and that scale and asking what the velocity increment, the statistics of the velocity increment on a smaller scale is. And this, the double condition is a black curve. The simple condition is a red curve. You can measure these, or you make the cuts. This is just fixing U2 and U3. You get the dots, and just fixing U2, you get the drawn line of your probability on the smallest scale. And then you can go on with mathematical tools and show whether this is correct or not, and you see this is really holding. But on the other side, you see that if you take here the line 0, and here's the line 0, you see that the maximum is shifting. So your conditional probability depends on U2. So this is not true, but this seems to be experimentally true. Okay. I think here, this is the main finding we got out in the last 10 years, I think. Because this is telling you with a sudden that this complex structure of n-scale statistics can be cooked down to the knowledge of only a single conditioned probability. If you make the construction like this, you only need to know on these points your velocity field. This is a 3-point correlation. If you make it to the right side, the same point u of x, and you have one r distance and the other r distance. So what this is saying, this is a 3-point statistics which is needed. If you know the 3-point statistics, you can figure out the end-point statistics in the sense of the increment. And I think this is experimentally, we have verified this 10 times, 100 times, no, not 100 times, I have not so much students, but several times. But it worked out quite nicely experimentally. And so I think this is an essential simplification of the complexity of turbulence. You can look at this also in another point of view. You can think about, put this into the picture of the cascade, that you have a disorder on that scale, which is going to a smaller scale and smaller scale and smaller scale. So what I said, that going down the cascade, you don't need to know what is happening on larger scales. You only need to know the last step. This you can bring in analogy to a stochastic process. Now a stochastic process running down the cascade from large scale to small scales. This is a little bit awkward. It's not running down time, but it's just, but formally, mathematically, here we are in Mathematical Institute, there's x equal t, and then it's the same. So in this way, I consider now, whatever a cascade is, Arkady is not here. So if I use the word cascade, we can start discussing. But you know what I mean. The common picture that big vortices are generating smaller ones, smaller one. And this process, how we go down, this one, I will now put into the box of a stochastic cascade process evolving in R. So my increment, UR, will be a function of R, or my probability distribution, my statistics on the large scale, will be now a function of R, which we consider always if we want to measure intermittency effects. Large scale, we have Gaussian. Going down to small scales, we go to intermittent distributions. Well, now I rushed through the theory of Markov process. Finally, you can read Kolmogorov's paper of 1931, 10 years before 41, 20 years before 61. So he wrote down all the theory on what you have to do with stochastic processes. Mathematics, it's called the Kolmogorov equation. Physics, we call it Fokker-Planck equation. And Fokker-Planck equation or Kolmogorov equation gives you a description how these conditional probabilities evolve if you change the distance r, if you come from one increment and let the other increment becoming smaller. And there are two terms which are important, a drift term and a diffusion term. And the nice thing is, if you can measure the conditional probabilities, you can estimate from experimental data the drift term and diffusion term.
Those U and R are vectors or scalars?
Pardon? It's scalars. You can do it. I do it at vectors at the end of my talk. At the moment, I just take the longitudinal increment. But you can extend this to a higher dimensional when these are vectors, when these are matrices. But this works in the same way. Okay, then we measure these increments. And here, if someone is reminding the talk just before, this is we have seen just before. If you look at this definition, what it is a conditioned variance on the conditioned on the fluctuation one step before. So these are the conditional moments we can measure. So fixing on one scale you are, and then you ask what is the mean value or the fluctuation, the variance of the smaller scale. So we have seen these quadratic plots just in the talk before. This is just the same. But here you have, if you go into the theory of stochastic process, you have to take this delta R against 0. This is a fusion rule somehow. But the point is, it's some technique. But if you have the conditional probability, you can measure drift and diffusion coefficient. This is nice. And if I can measure it, I can measure the Fokker-Planck equation. And if I have the Fokker-Planck equation, by the way, it's an instationary Fokker-Planck equation. These coefficients depend on R. If you have this instationary Fokker-Planck equation, you can solve it numerically. And here are in blue the experimental results, the PDF on large scales of the increment, the intermittent PDF on small scales measured, and the red lines are the solution of the Fokker-Planck equation. Or this is a conditional probability. The conditional probability, this is essential. This is the heart of turbulence. This is a 3-point correlation we need to construct all n-point correlations. This we can reconstruct also, or we can measure also, we can also numerically estimate by the known Fokker-Planck equation. And this coincides quite well. Well, here I'm now at this point that this n increment probability, joint probability distribution, can be expressed by the conditional probability, which can be grasped quite easily by a Fokker-Planck equation, which we can measure. There's one point still you may worry about. What is the role of u of x? With taking increments, we are somehow taking away the actual value u of x. Whether an increment happens at a large value of your velocity field or a small value, you are somehow filtered out by your velocity increment. The mean value is taken out. That's why we stepped in and made now the conditional probabilities condition in addition on a mean value of on a value of u of x at one point. You take the increment at one point, you just fix it. You take different values you measure, and then you compare the statistics, and you see you have different regions, you have less points, and that's why you only have to consider the points where they coincide, where you have. If you make a further condition, you get less points. That's why the less condition probability have more points and is more extended in the space. And with less points, you measure only this part. But here, they coincide quite nicely. So we can say also this does not depend on x. So I come to the point to n-point statistics and n-scale statistics. If you want to have an n-point statistics, you can express this by n increments and 1 point. You can make this by theory, and then I have indicated that it seems to be this doesn't play a role. and this way the joint increment statistics, and we have now the Fokker-Planck equation, with the Fokker-Planck equations, the conditional probabilities. In this way, the endpoint statistics can really be achieved by these Markov properties of the cascade. And I think this is an essential simplification. And the point is, by the trick to looking at this cascade as a stochastic process, there we get an essential simplification with the Markovian property that you have no memory, that there you need only the 3 points. But you must pay attention, we have the Markovian property, and if you have a Markov process, it has no memory, but it has correlation. So we need 3-point statistics in this way to get out the endpoint statistics, but definitely we have endpoint correlations. But the endpoint correlations can be expressed by 3-point statistics. So it is not saying you shouldn't mix it up. Turbulence has more than 3-point correlations. But we need in the cascade, we need the information, the memory. Each Markov process has long-term memory, but long-term correlation, but no correlation. So what correlation and memory is, that's the difference. So the point is we need the 3-point statistics to get all endpoint correlations out. This is something which caused also for me some long time troubles, but there you must make really a difference between memory and correlations. Well, some results, what we can do, if I know these endpoint statistics, I can also say, having measured these data, I can say the probability of the next point we expect, the new point, and we can estimate these probabilities and then make artificial new time series. So we have used these procedures 3 times for the same initial conditions measured, and then we get new time series. And we can analyze these time series. Again, we generate synthetic time series, and we analyze it with the same tool, reconstructing the Fokker-Planck equation and so on. And we see in these terms, the statistics, the conditional probabilities, and all are all the same in the generating synthetic time series as we had before in the measured time series. There's also a nice effect just to show what endpoint correlations you can get. If you take time series, which has less variation, you will see these joint the probability of the next point based on all these points, empirically estimated, is much smaller than if you have a flux which is much more turbulent, then the next time step is more turbulent. This is a case which is discussed in financial data volatility clustering. So if you have a turbulent spot, it is likely that the signal is going on turbulent. So you have a clustering perhaps of intermittency, and then no. And the interesting thing is, with this description, you don't have to have an instationary process. Your process, the stochastic equations, the Fokker-Planck equations remain constant, but because they can describe endpoint correlations, you can see these effects that your system, your turbulence is changing from a more violent to a less violent region, which is expressed in endpoint correlation. Okay, further insights. Length scales. We know turbulence has length scales, the integral length scales, Taylor length scales, dissipation length scale. Looking at these Markov properties, whether the double conditioned and the single conditioned probability are the same. This is only true if the increments are sufficiently far separated. If they are too close to each other, the distance between R1 and R2 are too small, we see that the double conditioned and the single conditioned probability are different. If they are far away, they are. So the Markov properties is only true in a special coarse graining of your cascade. If you go a step far enough down the cascade, you can imagine that some turbulence must somehow randomize that you can describe this in the stochastic process. But now this you can make a stochastic measure whether these statistics are the same, yes or not. And we have a Wilcoxon test, the value Q. If Q is 1, you can say, okay, with good confidence, the Markov property is fulfilled. Here it's not fulfilled. And then you take this length scale and compare it with the Taylor length scale or the dissipation length scale, Kolmogorov length scale, and we see a lot of experiment that it seems that this Markov, Einstein-Markov length is correlated, is 0.8, about 1 times the Taylor length, is the Taylor length. It's very closely linked to the Taylor length. So, that a stochastic process has a short time correlation length was already pointed out by Einstein, 1995, on his paper, famous paper on Brownian motion, where he said this Brownian motion description is only true if the time intervals we choose are sufficiently large that we can take the scattering as a somehow independent random process. And this is the same now for the picture of the cascade. As we go down the cascade, we must step sufficiently far down so that we can say, okay, how the turbulence is evolving, this we can take as a Markov, a random, a somehow stochastic process, which we describe by the diffusion coefficient. And this length scale seems to be the Taylor length. And it makes sense because the Taylor length, in my opinion, has some coherent small-scale structures. And if we have a small-scale structure still involved, and we take 2-point conditioned on it, we have chosen it, and with this, the simple and double conditioned probability not the same anymore. Okay. We can do the same analysis. I think here we have now an analysis tool which goes in more details. We now can think about what happens with the Reynolds number if we change the Reynolds number, and we see that these processes all change with the Reynolds number. Whereas if you take the other analysis, multifractal analysis and so on, you have the impression that there's some universal scaling behavior. Here we see it is all changing with the Reynolds number. And by the way, this D2, what in the talk before was shown, this square, this conditional variance, they had always an offset term. They had a quadratic part and an offset. And this offset you can show is violating the pure scaling behavior. If you put it in the Fokker-Planck equation, solve it, integrate it up for the structure function, you see the structure function is due to this term non-scaling. So there's always, that's why we have always difficulties with finding the proper scaling. There's a small term which is somehow, I have the feeling, at least in experimental data, whether this is coming from my sensors, I don't know, but this one is always violating a very a proper pure scaling behavior. Another type which was astonishing, we choose similar Reynolds number, a free jet and a wake, cylinder wake, and if we look at the R dependence of these coefficients for different Reynolds number, we see the funny result that the free jet seems to have a structurally different beta of R coefficient than cylinder wake. This would somehow say, even in the small scale statistics in my process, I still see the fingerprint of how my turbulence was generated. Because we look in a deeper way, we look at multi-point correlation, I get out that each turbulence, even the scaling may be similar, each turbulence has somehow a different, slightly different Fokker-Planck equation for the details of its statistics. And this would say universality, perhaps a very large Reynolds number, but we went up also to Reynolds number, a lambda of several thousand. Okay, but then there was recent time, we did some work together with Christos Vasilikos with a fractal grid, and there I was totally amazed. We changed the flow speed, we changed the Reynolds number, and here, neither the Markov length nor the stochastic process, the drift coefficients, and so on, they seem to be always exactly the same within experimental precision. So there seems to be, I think Christos will talk next day on this fractal grid and more, this fractal grid-generated turbulence seemed to have a single multi-scale feature. It seemed to be a special class, whereas if I take a jet, I take a cylinder, I always see in detail how the processes are changing from one Reynolds number to the other. It's running away. This fractal grid-generated turbulence, it's just one turbulence, that's it. And this was, for me, I don't understand whether I'm amazed about this result. I just want to put as a question mark, well, I think we still want to have some topics to work on in the next years. So, whereas in traditional turbulent generated experimental setups, I see always the fingerprint somehow of the turbulence, how it's generated, whether it's a jet, it's grid, or wake. We have found a new class of turbulence generated by a fractal grid, which has a property of turbulence in its fractality. And there it seems with a sudden that the Reynolds number dependence of these higher correlation statistics in this n-scale statistical description seems to be unaffected, seems to stay constant. Okay, I skip this, I just mentioned it. If you know the Fokker-Planck equations, you can make also the multipliers, and you can calculate the multipliers straight through. If you know these Fokker-Planck equations, then you can extract these also. And it is what was just Roberto Benzi just mentioned. You will see also the essential point for the multipliers is that the multipliers are not independent but dependent, and where you see some deviations. This you must take into account to get out the proper multiplier statistics. We have done also longitudinal and transversal. This was just a question. If you go multiply in two-dimensional in vectors, this gets a little bit more complicated. You need a little bit more data. So without 10 to 7, 10 to 8 data points, it's hard to get out properly these. But nowadays, it's not, you can do it. And then we get a two-dimensional Fokker-Planck equation. And there we found out a funny result that we know the transversal turbulence increments are more intermittent than the longitudinal one. And this we can express by our stochastic process, that the stochastic process in the transversal direction is just running faster, can be rescaled, than the other one. If we rescale it a little bit, where we are so far down in the cascade and the other one further down and put it together, they coincide. And so this gave us the idea to rescale. This is a sixth moment, ESS. There you see the longitudinal and the transversal structure function, which is more intermittent than the other. But if you start the rescaling by R2/3, they collide. But if this is the case, this can be only true if this is a non-scaling behavior, because if this is a pure scaling and you rescale, the scaling exponent shouldn't change. So this effect seems to be then what we figured out, and we saw also in the stochastic process, it is due to non-self-similar structures. There must be other non-scaling features which cause this result. Okay, I'm at the end.
Okay, lots of questions. Okay, let's start with it.
If there is a lot of questions.
Okay, so who wants? Okay, Della.
So you mentioned the universality in the results with the fractal grid. That D1 and D2, the Fokker-Planck functions, are universal. So how does it depend on the type of fractal? I mean, you can change a fractal grid and play with a fractal exponent, and to what degree is the universality then still kept?
Maybe. We have one fractal grid, and there we changed the speed, we changed the Reynolds number, and there for this one, we saw this is coming out. What it will happen if we change...
Remarkable, I think.
Pardon?
Pretty remarkable.
Yeah?
Charlie is next.
Related question. So you said for the grid, the wake, and the jet, the drift and diffusion depend upon the Reynolds number, but I couldn't tell from the plots, I couldn't read the labels. Do they look like they're converging to something as Reynolds goes to infinity? Or are they drifting off to...
We tried to figure out how fast they converge to fulfill exactly, for example, that the third moment is linear in R. And then we got out, to get the fixed point, we get out a Reynolds number of 10 to 8. So they are converging very, very slowly to get to a fractal behavior,
If they do converge to something, then whatever it is can only depend upon the Euler equations, right? So somehow they should be, these drift and diffusion coefficients should be derivable.
Maybe. Yeah, you're right.
Joachim, I was going to ask the same question about the dimension of the fractal, but you haven't done it. But did you try the active gradient between the...
We are working on the active grid. This is just what we are doing at the moment. It's exactly, we have the first signals and we start. So this analysis is, we have methods, but still you have to go through the data, and it is a little bit, you can't do it just in 1-2 days. You get results which you have to revise afterwards. So you have to go with verification and so on through. But I hope to in the next months to know what these, and if you take the active grid, this is also in this sense, but there you can change. If you don't drive it in a right way, which is corresponding to a fractal in a turbulent way, then definitely you get different answers. So I expect if you make a different fractal grid which doesn't have the fractality of the turbulence, then definitely you will run on another case. But it's an interesting case if you initiate the turbulent signature directly at the first moment at the creation, then something I think surprising may happen.
Okay, at the risk of keeping people away from their caffeine, I'm going to let Roberto have one last question.
Just to know whether, have you tried to apply this method for the passive scalar?
Not me, but it was Tutkun who has done it with Lusky, and they found interesting thing that I described everything by a Fokker-Planck equation, which is saying that the noise involved in the cascade is a Gaussian delta correlated noise. And in passive scalar, you get much more shocks, much more intermittency, and they found out that the fourth Kramers-Moyal coefficients don't converge to 0. So you have a noise term which is non-Gaussian, which is involved, which enhance, which make, in the theory of stochastic process, you get more shocks and more jumps inside, and this is somehow, I think, somehow fits together with the picture which we had for passive scalar, that this is making more singularities or something like this. So there you see differences, yeah.